Hi, within this lecture we're gonna see the final principle that we will be working on the qubits or the quantum computers, which is entanglement. We have already seen the superposition and the interference. Of course, we're gonna see what it means in the quantum computer world as well, but at least we understood the terms. Now we're gonna go into the entanglement. So when we talk about entanglement, we're going to talk about electrons. So what we see over here is actually an atom. Okay, so this represents an atom, and there are some electrons around it. And we can know the position of the electrons around the atom itself. So if you want to know a position about a person or like any object inside of the world, you can use several different measurements, right? For example, you can use a coordinate. So you can use a latitude and longitude, or you can use any x, y, z axes in order to determine a position of an object. Right, you can say I'm in this latitude, I'm in this longitude, and there is nothing else with me at the same exact latitude and longitude, because otherwise we would be merged into one, right? So electrons have the same principle as well. We can try to determine their location by looking at some kind of measures or some kind of coordinates. So it happens that there are four different measures or four different like values that we can look at when we try to determine the position of an electron. So as you can see, these four numbers are here, and first number is principal number. The second one is orbital angular momentum, so it kind of represents the momentum or angular momentum of the electron. So the third one is the magnetic kind of measurement, and the final one, and the one that we are interested in, is actually the electron spin. Of course, we're not going to go into the details of the other remaining three, because as I said before, this is not a quantum physics class, and I'm not a quantum physicist, so I'm not capable of telling you all about this stuff, but we have to understand the spin itself. So when you hear spin, you can always imagine the electron is spinning somehow, but in fact, electrons do not spin. Okay? So spin is something like that. It either has a spin up position or a spin down position. Okay? So you can actually measure this value to understand whether an electron has a spin up or a spin down. So if we measure this, of course we can understand that. But before measurement, in fact, we cannot determine the spin position. So it's actually in the superposition. So it's either spin up or spin down, or we can just say that it's in the both ways. It's either spin up or spin down, or it's in the both ways. But after measurement, we actually see whether it is a spin down or spin up. So we have seen the superposition before, right? So when we measure this or when we observe this, whole system collapses into some kind of state, and that state will be the spin up state or spin down state. So before measurement, we don't know it. Okay, so we can fairly say that it's either in the spin up or spin down, but it's in the actual superposition of spin up and spin down. When we measure, we lose the information before. Okay, so we don't know whether it was in spin up or spin down, it was in the superposition. We don't know it. We lose the information. And in fact, after we measure, if we measure again, if we get spin up for the first time, then we're gonna get spin up again. So if we get spin down for the first time, we're gonna get spin down again. So measurement collapses this into one state, and we get that state from onwards. So when you think of superposition, maybe you may want to think the Schrodinger's cat as well. So maybe you have heard the Schrödinger, the physicist, the infamous physicist before. So he came up with that analogy like many years ago. He said that there is a cat in a box, okay, and we put like a radioactive substance near it. So there is a cat and a radioactive substance in a box, and that box is closed. So there is a 50% chance that this radioactive substance will decay, but we don't know it. So if it decays, if it actually poisons the cat, of course the cat will die. So he says that before opening the box, cat is in a superposition of being alive or dead. So once we open the box, we know the result. So maybe this is an analogy that may actually help you understand the superposition in a better way. But again, so this is just an analogy. What we are actually interested in over here is the spin up and spin down state, because we can associate this with like a bit value of 1 and bit value of 0. So 0 for down, 1 for up. And by the way, in real quantum computers, we're not always going to work with quantum mechanics. Eventually it will collapse into some state, and we're gonna have to get the details in a classical bit. Okay, so it's gonna either be 1 or 0. So it's either going to be spin up or spin down at the end of the measurement. So anyway, we're gonna have to talk about entanglement a little bit. So physicists have discovered that when two electrons interact with each other, they can be in like a setup called entanglement. So they are entangled with each other, which means that their spins have actually some kind of correlation between them. So if you measure one electron, it will be spin up, and the other one will be immediately spin down. Okay, so it doesn't even matter where they are located. So if they are interacted with each other, and if you take one electron to the space, and if the other one stays on the earth, when you measure the one on the earth, the other one at the space will be immediately spin down. Okay, it's even faster than the speed of light, because it's instantaneous. Okay, so of course this didn't make sense when Einstein actually discovered that, and he called it spooky action at a distance. So maybe you have heard that term before as well. So it's immediate, it's weird, and it has to do something with the quantum mechanics as usual. So we can actually use this phenomenon, use this thing in order to entangle the qubits, okay, so they can have correlation between them. So in the case of electrons, they can be spin up and the other one will be immediately spin down, but we can correlate them in a way that they can be both up and both down. So we can have the same result in a series of qubits, or in a series of electrons, for example, and it can actually increase the possibility that we can do like very big calculations in a very short time. So this is one of the things that we have to focus on, that we have to understand how to work in qubits or how to work in quantum computers, so that we can actually leverage this idea, leverage this potential. So again, entanglement is just a correlation between two qubits or two electrons or two photons. So you can measure one of them and the other result will be immediately known to us. So there is another analogy for that. For example, you know that you only have one apple and one banana in a box, in two separate boxes. If you open one box and you see banana, then you immediately know that the other one is actually apple. So it works like this. When you just measure one, you immediately know the result of the other one. You don't even have to measure it. You don't even have to open the box and look at it. So consider this analogy when you want to remember how entanglement works as well. So that's it for the entanglement. We're gonna stop here and we're just gonna go into the qubits and measurement in the following lectures.